Hello, my name is Dorian Leroy and I will present the work we did with Benoît Lelandais, Marie-Pierre Oudot and Benoît Cammal in our paper titled Money Logging for Executable DSLs. Analyzing the behavior of complex or data-intensive systems requires insightful data. Two widespread techniques to gather such data are logging and runtime monitoring. Logging revolves around extracting data from the execution state of a program and formatting it in readable form. Runtime monitoring is concerned with the evaluation of temporal properties over the execution of a program. Both techniques are most often used in a language-specific way. This can be through language constructs such as printf in C, or this can be through language-specific libraries such as log4j in Java. This is acceptable for general-purpose languages as they can address a wide range of concerns. However, the situation is different in the case of domain-specific languages, DSLs for short. DSLs allow to bridge the gap between the domain expert and the software realizing their models. To achieve this, they rely on the reification of the domain's concept as a language and on an ecosystem of tools to edit, manipulate, and analyze models and generate artifacts from them. Executable DSLs go one step further by defining an execution semantics. This enables the provision of tools for dynamic analysis, such as interactive debugging and testing. NabLab is one such DSL, which reifies the concepts of numerical analysis in a language targeting numerical analysts writing multiphysics simulations. The abstract syntax of NabLab is defined as a metamodel listing those concepts and the relations between them. The execution semantics of NabLab is divided between model state on the upper right and execution rules on the lower right. The model state extends the metamodel by adding dynamic data, the values of variables in the case of NabLab. The execution rules provide the execution semantics of each concept of the metamodel and allows to obtain an interpreter for the language. Here is an example of NabLab model solving the heat equation using an iterative numerical method. This model contains two nested loops, an inner loop over k and an outer loop over n. With the numerical method used, the inner loop refines the computed temperature over and over until a so-called residual variable becomes small enough. The model then proceeds to the next iteration of the outer loop, starting the simulation of a new time step. One property we want to check in this model is that the residual variable decreases from one inner loop iteration to the next and is reset to a higher value once the outer loop starts a new iteration. However, the facilities available for performing dynamic analysis on NabLab models are limited and make this impractical. The output capabilities of NabLab are first and foremost designed for production use. As such, they are impractical for debugging, where some flexibility is required to allow the domain expert to investigate the origin of a defect. And while interactive debugging support could be used for NabLab models, it would be impractical for checking such a property. Thus, a preferred approach would be to perform logging and monitoring of the desired property. However, a few obstacles stand in the way of domain-level logging and monitoring. The first obstacle is that the expressivity of DSLs can be very restricted. This means that language constructs necessary to support logging and monitoring, such as printing or conditionals, might need to be introduced into the language, which goes against the principle of separation of concerns. In addition, logging and monitoring may require a different expressivity, such as statistical operators over arrays, than the expressivity of a given language. A second obstacle is the domain specificness of DSLs, which impedes the reuse of existing libraries and incurs additional costs to adapt such libraries or to develop domain-specific ones from scratch. Moreover, logging and monitoring are often dependent on one another. For example, monitoring can operate on data derived from the execution state through logging mechanisms. In return, the logging behavior can be triggered or altered when monitor properties are validated or violated. Yet, leveraging these complementarities also proves challenging for users of DSLs, should they have access to logging and monitoring facilities. That's because domain-specific facilities must also be interoperable at the domain level for domain experts to leverage these complementarities. Otherwise, they would have to deal with software level integration details. To address these challenges, we propose Monilog, a language agnostic framework under the form of a language unifying logging and monitoring. Monilog allows domain experts to define loggers and runtime monitors and combinations of the two, which we call Moniloggers. I will now provide an overview of the approach before presenting the language in more details. On the upper left of this figure is an executable DSL defined through its abstract syntax and operational semantics. This DSL also provides an instrumentation interface which exposes the instrumentable concepts in the DSL, such as functions, methods, statements, assignments, and so on. The instrumentation interface also exposes the subset of the execution state that can be accessed from instrumented code. From this DSL definition, an interpreter is obtained which is able to execute models conforming to the DSL. This interpreter itself runs on an execution platform such as a JVM like Hotspot or GraalVM. In this context, Monilog comes as a language to define Moniloggers for models. Monilog relies on the instrumentation interface provided by the executable DSL to allow language users to manipulate its domain concept. Moniloggers are executed by the Monilog interpreter, which runs on the same execution platform as the DSL interpreter. Moniloggers are defined according to the event condition action paradigm, allowing to specify when a monilogger should trigger, whether it should trigger based on the execution state, and what it does when it is triggered. To allow the Monilog interpreter to instrument executions of the DSL interpreter, a dynamic point-cut implementation is obtained by combining Monilogger definitions and the instrumentation interface of the DSL. This allows to bind the execution of functions, statements, assignments, and so on to the events that are declared in a Monilogger. I will now present Monilog in more details before discussing its two implementations. The main concepts of Monilog are events, expressions, and actions. By manipulating these three concepts, users can define Moniloggers that trigger on domain-specific event occurrences, that execute if certain domain-specific conditions are satisfied, and that extract data from the execution state, whether to log it or to evaluate properties over the execution. Events can be execution events exposed by the instrumentation interface and emitted when a given execution rule is called. Alternatively, events can be defined within a Monilog specification and emitted by a Monilogger. Expressions are used in the conditions and actions of a Monilogger. The usual numerical and Boolean expressions are supported and not shown on the meta model. Note that assignments to variables of a Monilog specification are also expressions. Atomic expressions include references to the execution context of the model and references to variables declared as part of the Monilog specification. Atomic expressions also include calls to other languages that are supported by the execution platform of the Monilog interpreter. Finally, atomic expressions can be calls to layouts, a kind of model element that is responsible for transforming its inputs into strings. Monilog comes with a string layout, which allows to format strings as one would in Java, but additional layouts can be provided as extensions to the language. Actions are executed when an event occurrence triggers a Monilogger and its condition is satisfied. An action can consist in evaluating an expression, emitting a user-defined event, starting or stopping a specific Monilogger, and calling an appender. Appenders are a kind of model element responsible for sending messages to their destination. Monilog comes with a file appender and a console appender, and more appenders can be provided as extension to the language. I will now go over an example Monilog specification aiming to monitor the behavior of the iterative heat equation NABLAB model presented before. To monitor the property of the residual variable, we introduce a Monilog variable called previous residual, which will be used to store the value of the residual variable in the previous iteration over k. We then declare the events of interest, calls to the job that updates the residual variable, and calls to the job marking the end of an outer loop iteration. Every time the residual is updated, we check that its new value is lower than the previous value. If that is the case, we log the values of interest to the console and update our previous residual value with the current one. Otherwise, we log an error message and stop the money loggers involved in monitoring the invariant. Finally, when an outer loop iteration comes to an end, we reset our previous residual variable to an upper bound value. I will now quickly present our two implementations of Moneylog before talking about the evaluation of the approach. The first implementation is the AspectJ implementation. It is applicable to Java-based interpreters and is non-intrusive with regards to the language definition. This means that we don't have to adapt the operational semantics to provide the instrumentation interface of the DSL, as it is provided through weaving aspects into the interpreter. We can here see the aspects used to allow for the instrumentation of calls to job elements. The second implementation is a truffle-based implementation, which relies on GraalVM as an execution platform. It relies on the instrumentation framework of the Truffle language implementation framework, and thus can be used with any truffle-based interpreter, such as JavaScript, Python, or R. It can evaluate calls to any language installed on the GraalVM. However, it requires the instrumentation interface to be part of the language definition. For example, this snippet of code shows that the implementation of NabLab variable assignments implements the instrumentable node interface, as well as the hashtag method, which allows the instrumentation framework to detect AST node that perform assignments in a generic way. To evaluate our approach, we answered two research questions. To answer the first research question, we investigated whether Moneylog allows to leverage the complementarities between logging and monitoring. We answered this research question through demonstration cases similar to the illustrative example. To answer the second research question, we conducted a performance evaluation of our AspectJ and Truffle-based implementations of Moneylog. I will first detail one of our demonstration cases and then provide more details on the performance evaluation. So in this Moneylog specification, which targets the NabLab model solving the heat equation, the aim is to change the interval at which logs are produced according to the standard deviation of the UN variable, which represents the computed temperature at a given time step of the simulation. Initially, logs are produced at an interval of 0.0001 in terms of simulated time. But once the standard deviation of the temperature goes below 0.2, we increase that interval to 0.01. In this specification, monitoring happens over data derived from the execution state, and in return modifies the logging behavior when the monitored property is validated. This shows one way the complementarities between logging and monitoring can be leveraged by using Moneylog. The performance evaluation was conducted on the following setup and consisted in executing an NabLab model with and without instrumentation with Moneylog. We measured the overhead induced by three different Moneylog specifications on various execution times. The AspectJ implementation was evaluated over the Java-based NabLab interpreter, while the Truffle-based implementation was evaluated over the Truffle-based NabLab interpreter. As shown on the slide, the absolute overhead is reasonable for the shorter execution times, as it is situated around 8.75 seconds for AspectJ and 2.75 seconds for Truffle. On longer execution times, the relative overhead decreases by a bit less than half, stabilizing around 60% for the AspectJ implementation and 19.5% for the Truffle-based implementation. Overall, we deem the approach suitable for debugging and testing, in particular considering how NabLab makes intensive use of money logging, being a language with highly iterative models. So in conclusion, we propose Moneylog, a new language to define loggers, runtime monitors, and combination of both. Moneyloggers are defined in a language-agnostic way, relying on the instrumentation interface provided by executable DSLs. As a unifying framework, Moneylog allows domain experts to leverage the complementarities between loggers and runtime monitors. In terms of future work, We plan to explore Monilogging for compiled DSLs, as well as editor support for polyglot language calls.